Hi friends, welcome to the channel. In this video, we are going to discuss about the tetravalency of carbon and hybridization. So let us understand tetravalency of carbon. So tetravalency of carbon means that carbon has a valency of 4 and it can make a maximum of 4 bonds. So let us understand about that. Now we know that carbon is having an atomic number 6 and a mass number of 12. So if we are writing the electronic configuration, it is 1s2, 2s2, 2p2, 2p2. Okay, so this is the this is the configuration of carbon. Now let us draw the box diagram. The box diagram. So here we have 1s, here we have 2s, and here we have 2p. So in 1s there are 2 electrons with opposite spins. In 2s also, and in 2p we have 2 electrons. Okay. Now if we observe this box diagram, we can see that there are only two unpaired electrons. There are only two unpaired electrons. There are only two unpaired electrons, and from this we understand that valency of carbon is 2, but that is not true. There are only two unpaired electrons. This shows that valency of carbon is 2. But carbon is tetravalent. Carbon is not having valency 2. It is tetravalent. So it is believed that during scenario of bond formation, carbon is in its excited state. This is very, very important to understand. Whenever a bond is formed, carbon is in its excited state. So let us first write the configuration of carbon. So the configuration of carbon is 1s2, 2s2, and 2p. You can write 2px1, 2py1, and 2pz0. Okay, this is the configuration of carbon. Now if I am drawing the box diagram, it will be 1s, 2s, and finally 2p x and 2py with one electron each. Now carbon in its excited state, listen carefully, carbon in its excited state, what happens is one electron from this will move here. From the 2s, one electron will move, and the carbon's configuration in its excited state, carbon in its excited state becomes 1s2, 2s1, 2px1, 2py1, and 2pz, sorry, z1, 2pz1, 2pz1. Okay, so if we have to draw the box diagram, so in the box diagram, this will be 1s, so there will be two electrons over here, and this is 2s. In its excited state, it has only one electron. Then we have the 2px, 2py, and the 2pz, where there are one electron each. So this is carbon in its excited state. And now if we observe clearly, we can see that there are four unpaired electrons. There are four unpaired electrons. So in excited state, it has four unpaired electron and its valency is 4. So during bond formation, the carbon is imagined or is believed to become in to be in its excited state. Now organic chemistry is basically a case study. Something has happened, experimentally we determine that and we find a reason for that. So this is also a similar case. So carbon is believed to be in excited state during the formation of bond or during the bond formation. Okay, now let us move ahead to the next section, that is hybridization, which is very, very important. So To understand hybridization, now there is a basic definition for hybridization, that is hybridization is a mixing, is a phenomenon in which atomic orbitals mix with each other and it forms hybrid orbitals with equal number of hybrid orbitals with equal energy. Now, to understand hybridization, let us take an example for CH4. Now, this is discussed in detail in the chapter chemical bonding, but related to organic chemistry, we will discuss about hybridization. So, taking CH4 as an example. So, let us take CH4 as an example. So, I'm going to write carbon in its excited state. Here, I'm going to write carbon in its excited state. Carbon in its excited state. So, in its excited state, there will be two electrons in 1s, one electron in 2s, and then one electron each in 2p, x, 2py, and 2pz. So 2px, 2py, and 2pz. Now, if the atomic orbital of hydrogen, that is 1s orbital of hydrogen, overlaps, so in CH4 there are four hydrogens. So one hydrogen will come and overlap here. One atomic orbital of hydrogen, that is 1s orbital, will come and overlap with 2s. For the second hydrogen, it will come and overlap with 2p x, third 2py, and fourth 2pz. So the four hydrogens have come and overlap and they have made bond. Now from this, by observation, we can see that in CH4, one CH bond is formed by one S and two, sorry, this is S, this is S, one S and two S overlapping, that you can see in this. 1s and 2s overlapping has led to formation of one carbon hydrogen bond, and three carbon hydrogen bonds have been formed by 1s 2p overlapping. 1s 2p overlapping has led to formation of three carbon hydrogen bonds. So if in CH4 there are four bonds, CH4 there are four bonds. So according to this, we can understand that one bond is different from the three others. So three bonds are identical to each other and one is different from the others. So from this we understand, this shows that in CH4 three bonds are identical and one is different. Shows that three bonds are identical and one is different. But experimentally that is wrong. Experimentally, it was determined that all four bonds in CH4 are identical. It is not the case that three bonds are identical and one is different from the three. That is not the case. In CH4, all the four bonds are identical to each other. Now, this is only possible if atomic orbitals mix, if there is a mixing of orbitals to form four hybrid orbitals. So, four hybrid orbitals have to be formed. Then only four hydrogens can come and overlap, right? So, four hybrid orbitals have to be formed and they have to be identical to each other. And this phenomenon is known as hybridization. So, experimentally, in CH4, all four bonds were identical to each other, and this was only possible if the orbitals mixed together and they formed four hybrid orbitals which were of equal energy and are identical. So here I'm going to write carbon in its excited state. So this is my 2s orbital. So there is one electron in it. Then there are one electron each in the 2p orbital. So this can be taken as 2px, 2py, and 2pz. Now all those orbitals will mix together. All those orbitals will mix together and form four hybrid orbitals of equal energy, and the hybridization will be sp3 hybridization. I believe you know the basic of hybridization, that is types of hybridization. We have sp3, sp2, sp3d, sp3d2, etc. But in organic chemistry we'll be discussing about sp3, sp2, and sp hybridizations mainly. So these orbitals will mix together and they form four hybrid orbitals, and these four hybrid orbitals are having a hybridization of sp3. These four orbitals are having a hybridization of sp3 and the four of them have one electron each. one electron each. Now the 1s orbital of hydrogen will come and overlap. Of the four hydrogens will come and overlap, and you can clearly see that these four are identical to each other, and therefore the four bonds are identical. So experimentally it was determined that four bonds are identical, and this was explained by the concept of hybridization. Now, how to calculate hybridization? Now, in the exams, they ask you a question. They give you a compound, and they ask you to find hybridization of any one of the element in that compound. So, hybridization can be calculated by a simple formula, that is number of sigma bonds plus lone pair of electrons. Number of sigma bonds attached to that particular element, and the total number of lone pair of electrons. So this very simple formula can give you the hybridization. So let us take few examples regarding to that. So the first example we are going to take is a simple compound, that is CH3CH3, and here we are told to find the hybridization of the first carbon atom. So first step is to count the total number of sigma bonds. Now counting total number of sigma bonds is very easy. So let us count the number of sigma bonds. So we have to count the number of sigma bonds for the first carbon atom only, because we are told to find the hybridization of this carbon atom. So the total number of sigma bonds attached to that carbon atom will be equal to 4. 1, 2, 3, and 4. So I have got the answer as 4 plus lone pairs, that is equal to 0. So my answer is 4. Now if this value, listen carefully, if this value you calculate is equal to 4, then the hybridization is sp3. If it is equal to 3, then the hybridization is sp2. If it is equal to 2, then the hybridization is sp. So the answer we got here is 4. This means that the hybridization of this atom, of the element carbon, is sp3. Okay, now example 2. CH 2 double bond with CH single bond with CH3. So we are told to find the hybridization of the second carbon atom. So it is very simple. First step, just count the total number of sigma bonds. So when you count the total number of sigma bonds, you get 1 and 2, 3. Answer is equal to 3, plus there is no lone pair, equal to 0. So hybridization of that carbon atom is sp. So now counting of sigma bonds is very easy. Like you have a carbon hydrogen bond over here. This is a sigma bond. Now from the double bond, one will be sigma and one will be pi. So 1, 2, and 3. So 3 sigma bonds. So 3 plus 0, the hybridization is equal to sp2 hybridization. Okay, now let us take the third example. So example number 3, CH2 double bond C double bond CH2. Now we have to find the hybridization of the second carbon atom in this question also. The second carbon atom. Okay, the first it's a very simple method. You just have to count the total number of sigma bonds. So here you can clearly see that from this double bond, one will be sigma, one will be pi. So from here you have one sigma bond, and from here also you have one sigma bond. There is no other sigma bonds attached to this carbon atom. So the answer to this question is 2 plus lone pair is equal to 0. Therefore hybridization is sp. Now let's take the next question. Question number 4. Okay, we'll take very simple examples, not much complicated ones. Okay, so I have a nitrogen double bond CH single bond CH3, and here I have a CH3. So I have to find the hybridization of nitrogen. Okay, the hybridization of nitrogen. This is also very, very simple, but you have to remember one thing, that nitrogen is making only three bonds. That is, there is a lone pair over here. Is a lone pair over here. So count the total number of sigma bonds, 1, 2. So total number of sigma bonds is equal to 2, plus there is one lone pair, therefore 3, and the hybridization is equal to sp2. The hybridization of nitrogen is sp2. Now, fifth question. This is a very simple question again. You are taking NH3. NH3. Now in NH3, remember there is a lone pair on nitrogen, and therefore hybridization will be sp3. Am I right? There are three sigma bonds, 3 plus 1 lone pair, therefore 4, and the hybridization is equal to sp3. Now a sixth example. Now this is some kind of a special case. You have to, we'll understand in detail about this in the chapter General Organic Chemistry when we are discussing resonance. Now, this is the question, NH2, and on nitrogen we have a lone pair, obviously, right? Now, if you have to calculate the hybridization of nitrogen, then we have 3 sigma bonds plus 1 lone pair, and that is 4, and the hybridization should be sp3, but that is wrong. The hybridization of nitrogen in this compound is not sp3, but it is sp2. Why? Because this lone pair is in conjugation, and it is taking part in resonance. We will understand in detail about conjugation and resonance in the coming chapters in general organic chemistry, but for now just know that this lone pair is in conjugation and takes part in resonance. Now when the lone pair takes part in resonance, we don't count it in the case of hybridization, so we do not need to count this lone pair in the case of hybridization, and therefore you'll get the answer as 3, and the hybridization is sp2. Hybridization is sp2. Okay, so these are very, very simple examples regarding to hybridization. So now let us look at some important points. The first point is bond length order. Bond length order, it's very important. sp hybridization forms the shortest bond. So the order of bond length is sp3 greater than sp2 greater than sp. Talking about electronegativity, now what is the reason? What is the reason for bond length order to be sp3 greater than sp2 greater than sp? Now this all depends on the s character. Now if we look at if you look at sp, the percentage s character is equal to 50 percentage. The percentage s character is equal to 50 percentage, and in sp2 it is comparatively lower, in sp3 it is even lower. So when the percentage s character increases, what happens is that bone electrons are more attracted towards the nucleus, because the s is closest to the nucleus, and that is why the atoms will be more attracted to each other, and due to that what happens, the bond length decreases. Now talking about electronegativity also, you have to this is a very simple thing to remember, that electronegativity is directly proportional to percentage s character. Electronegativity is directly proportional to percentage s character, and that is why sp is having the highest electronegativity, then sp2, and then sp3. Now talking about bond energy is inversely proportional to bond length. Now therefore the bond energy order will be sp greater than sp2 greater than sp3. So these three are very, very important points. First, bond length order, electronegativity order, and then the bond energy order. So that's it for this video. If you like the video, please like, share, and subscribe to the channel. Thank you.